let's do the official welcome here since I just put the recording on. All right, so again, we're going to be talking about batteries, and then we're going to talk about electrolysis. All right. Wanted to point out, I don't know if you saw my message on the chat box, that I updated the PowerPoint notes a little. It looks like a lot, but it really is a little. So if you want to take a little time to go and download the new version, that's fine. But don't worry if you can't do it now, you can do it later, and just go back to the recording and fix whatever needs to get fixed. All right. Okay, so let's go ahead and look at what we're doing here. All right. So let's rethink the electrochemical cell. Remember, we started out by talking about something we call electrochemical processes, part of which was, how do I use an electrochemical reaction, oxidation reduction reaction, essentially, to derive useful energy. So there are several things that we would like to have here. Number one, we want to be able to capture energy efficiently. I don't know if we mentioned this when we reviewed the concepts of energy in the previous unit. We used the example of the reservoir and the dam and opening the floodgates and using the flowing water to move a turbine and capture electricity. The reality is that we only capture a very small percent of that potential energy that was stored in the water at the high altitude. So we need to have something that captures energy more efficiently. We'd also like something portable. The electrochemical cells that we have been showing you on the previous lectures, two beakers with two pieces of metal stuck in them, connected by wires, and then a little piece of plastic tubing between them, doesn't seem like a very portable idea, does it? And then we have the idea of rechargeability, the idea that we don't want this thing to just simply run out. We'd like to be able to recharge it and keep using it. I mean, that is what we do with our computers, with our phones nowadays, right? And nowadays, with the coming of, Tesla or other electric cars, of course, we'd like that, right? So these are some of the design features in a typical electrochemical cell. Remember, first thing we need a spontaneous redox reaction. And we want to keep that in separate compartments so that we can run the electrons through an outside circuit and capture that electric current, right, as energy. Now, we need a way to transport the electrons. In the electrochemical cell, we just had wires, but like I said, the galvanic or electrochemical cells that we showed you before are very unwieldy in terms of moving them around. Now remember, that very important thing was we needed a solid surface for the ions to deposit as they are reduced. For example, in the cathode, where the ions in the electrolyte solution are getting reduced to the metal, we need a surface where they can deposit, so that instead of having a random, totally unorganized group of atoms, we actually are carefully layering them onto a piece of metal. And of course, we need a medium for the electrolytes to exchange. In the galvanic cells that we showed you, we had a salt bridge, but like I said, that's very unwieldy as a form of portable energy. All right. So what we'd like to do, therefore, is we would like to work with batteries. And how about if we do this? I want to take us back to some old school movie here. I hope you guys all remember The Matrix, one of the best sci-fi movies ever, wasn't it?
You mean artificial intelligence?
A singular consciousness that spawned an entire race of machines. We don't know who struck first, us or them, but we know that it was us that scorched the sky. At the time, they were dependent on solar power, and it was believed that they would be unable to survive without an energy source as abundant as the sun. Throughout human history, we have been dependent on machines to survive. Fate, it seems, is not without a sense of irony.
The human body generates more bioelectricity than a 120-volt battery and over 25,000 BTUs of body heat. Combined with a form of fusion, the machines had found all the energy they would ever need. There are fields, endless fields, where human beings are no longer born. We are grown. For the longest time, I wouldn't believe it. And then I saw the fields with my own eyes. Watched them liquefy the dead so they could be fed intravenously to the living. And standing there, facing the pure, horrifying precision, I came to realize the obviousness of the truth.
What is the Matrix? Control. The Matrix is a computer-generated dream world, built to keep us under control in order to change a human being into this.
Right? That is what the Matrix is about. Well, I hope you enjoyed that little clip there. Like I said, one of my favorite sci-fi movies of all time. Anyway, so let's look at the design of a battery. I'm not going to go deep into stuff here, but I just want you to see a little bit about it. So this is what is typically called a dry cell or Leclanché cell. This is a design, or let's say a sketch, of the battery that Morpheus was showing Neo in that clip of the movie, and that I showed you at the beginning of our lecture today. Notice the components here, all right? Let's start out with the bottom. Notice that we have a zinc anode, right? That is where the oxidation happens. That is the source of electrons. And because it's the source of the electrons, we call that the negative pole. Notice that those electrons are going to be traveling around. And once you get the thing connected, like when you close the circuit, right? When you put this inside a machine and you're in here, right? And, oh gosh, somebody's in the waiting room. Come on, guys. Hold on a second. Okay, as I was saying, the anode is a zinc. It has a negative on it because that is the source of the electrons. When the circuit is closed, the electrons will flow to the cathode. Notice that the cathode has several parts. First of all, it has a rod of graphite in the middle, and that's the positive pole or whatever of the battery. And that is that little stub that you see on the positive end of a regular battery, right? Notice that there's also in there a layer of manganese dioxide, a paste of zinc chloride and ammonium chloride. Those are your electrolytes, and a spacer in between them. So let's see what the reactions are in a typical, what we call a dry or Leclanché cell. All right, let's go ahead and do that. And let's look first of all at what happens at the anode. So at the anode, you have zinc being oxidized into zinc ions, releasing electrons, which again, when the circuit is closed, or let's say when the battery is in the device and you turn the power on, electrons are going to flow to the cathode. They are initially captured by the graphite and taken over into that layer of manganese dioxide that is sort of like held in a moist paste of zinc chloride and specifically ammonium ions. And this is the reaction at the cathode. All right. And so if we add those up, you can see where the electrons will cancel out and you get a major reaction going on here where zinc is being oxidized, the manganese is getting reduced, and the ammonium ions are also being converted to ammonia. Don't forget, The conversion of ammonium is not a redox reaction. There is no change in the oxidation state of nitrogen there, all right? So don't forget that. Acid-base reactions are not redox reactions. So that is essentially the functioning of a typical battery. Of course, what I'm going to do is let me give you some ideas about other ones. These are some of the slides that I added that were not in the original slideshow here. And let's see what we got here. So let's look at some variations on these things. The first one is the alkaline battery, which is perhaps one of the more common types of batteries that we buy at the drugstore or electronics store or whatever, right? So in this case, the anode, again, is a zinc, but in this case, you have it in a basic environment. The product is still a zinc oxide, but what happens is at the cathode, you don't have the ammonium ions. You basically are producing hydroxide ions. What will happen here is the reason why alkaline batteries are, more in demand nowadays is because in the basic environment, the anode, the zinc anode, corrodes less rapidly, and so the batteries last longer. You probably remember the old school batteries, the cheapo batteries out there. After a while they corrode, they get all rusted out, and they leak some acid stuff in them. Usually alkaline batteries don't do that. Of course, over a long period of time, yes, they might. So this is the reason for alkaline batteries. They last longer. Now, if you really want a long-lasting battery, you go to the mercury electrochemical cells. And in the mercury, what you have is, again, you have a zinc anode in a basic environment, but your cathode is an oxide of mercury that gets converted to mercury itself. Again, the basic environment gives you a more stable, less corroding anode. But the other thing that happens here is that when you add up the reactions, realize that the net reaction does not involve a change in the electrolytes. There's no net change in electrolytes here. And because of that, this is a very, very long-lasting type of battery. These are the types of batteries you use for things like pacemakers or hearing aids, where you need the power to last for a very, very long time. Okay, another variation is, oh, sorry, that article there is kind of wrong. Here is the nickel-cadmium battery. And in the nickel-cadmium battery, you have cadmium as the anode and then a nickel oxide as the cathode. And again, of course, these are the kinds of batteries that can be recharged. But nowadays, the ones that are really in vogue are the lithium-ion batteries.
Lithium-ion battery is the power source for modern electric vehicles. These days, everyone has heard of lithium-ion batteries. But what makes them so special? First of all, each battery is made up of many smaller batteries called cells. Let's take a closer look at one to see how it works. The electrical current reaches the cells via conductive metal surfaces, in this case aluminum foil on one side and copper foil on the other. And just as in every other battery, there is a positive and negative electrode called the cathode and the anode. The cathode, or positive electrode, is made of a very pure mixed metal oxide containing lithium. The more uniform its chemical composition and crystal structure, the better the performance and the longer the battery life is. As you would expect, the anode or negative electrode is located on the other side. It's made of graphite, a natural form of carbon with a layered structure. The battery is filled with a transport medium, the electrolyte, so that the lithium ions carrying the battery's charge can flow freely. This electrolyte must be extremely pure and as free of water as possible in order to ensure efficient charging and discharging of the battery. To prevent a short circuit, there is an insulating layer placed between the two electrodes, the separator. To the tiny lithium ions, the separator is actually permeable. The experts call this property microporosity. Let's take a look at what happens when a battery is charged. The positively charged lithium ions pass from the cathode through the separator into the layered graphite structure of the anode, where they are stored. Now the battery is charged. When the battery discharges, that is when energy is removed from the cell that can be used as electrical energy outside the battery. The lithium ions travel via the electrolyte from the anode through the separator back to the cathode. The electric motor converts this electrical energy into mechanical energy, making the car go. The total amount of energy available in the battery, the maximum speed of making this energy available, but also how long the batteries last, is closely related to the quality of the materials used. To sum it all up, higher quality, pure materials, along with customized formulations, lead to improved battery performance and longer battery life. BASF Battery Materials business is strategically focused on cathode active materials with leading technology and a comprehensive portfolio. The advanced products and continuous research improve the performance of the batteries and at the same time help to reduce the costs per kilowatt hour, making them more affordable and widely available in automotive drivetrains. The key for reconciling individual mobility with the global need to reduce emissions and improve air quality. BASF. We create chemistry.
Got a little commercial in there, didn't we? Hey, but I thought it was a really cool video. That's why I wanted you to see it. All right.